Hello, everyone.
Yeah.
Hello, everyone. Welcome back to the afternoon session. We're glad to have Vladimir Fock to talk about phases of higher laminations.
Okay, thank you very much. And really, it's a pity that I could make to you. I see how you discussed at the Blackboard. I really feel really sorry not to be among you. And well, but on the other hand, I would like to say that with Sasha, it's not unusual because very big and not the worst part of my life I spent with a telephone in my hand, walking around and talking to Sasha. And well, continue this talk as a continuation of this phone conversation, and hopefully I'll see Sasha very soon and we'll continue directly. And so, well, the subject is high laminations, which we discussed with Sasha a million of times at all different aspects of that. So, and well, I don't know. Well, it's usually for him, perhaps it's not a very new subject. Also, I'm sorry for that because it's well, but nevertheless, it seems to me, well, I understood something about that. It's maybe not very new, but at least for me, it was a kind of amazing, some amazing observation, which I want to share with you. So just to recall what all that is about. That what's the problem about higher laminations? Well, I recall that well, we speak about cluster approach to local systems, and well, we speak about the space X of the X or A, which I'll interchange from time to time, just not to go to the details. We fix a group G and the local systems on the surface sigma, which is a surface with perhaps which is decorated by punctures and with points on the boundary. So the related surface, and well, and also we should fix some semi-field over which this space is considered. So this is a space of local systems on sigma with semi-field F is semi-field, which can be field. Oh, sorry. It's a main object of the study, and well, I'll will not write G and sigma anymore. So if I consider chi of I can consider chi of C is just normal space. So local systems over C or over R is over field. But if you consider Q of C is just complex local systems, chi of R is a R positive, is a semi-field, because you can add, multiply but not subtract, is an analog of Teichmüller space, higher Teichmüller. And chi of chi of tropical, which can be R tropical. So R tropical is just a semi-field of real numbers with respect to max plus operations. So chi of T, or it's just the space of what is usually called the space of laminations. They're all what is a single lamination is not very clear. So I am going to address this question. So space of laminations. And the main question which I am addressing now, what is the, we know what the space of laminations, but over R, and well, and also there is a version which is ZT. ZT is also a semi-field with respect to addition and maximum. And this is a space of integral laminations. And this is discrete space and most interesting. So just recall that for if G is a for G equals SL2, the space of laminations chi of ZT is the collection of curves of not self-intersecting curves of sigma. So this is you imagine that this is, well, I am not speaking, well, there are some details concerning the punctures and the mark points, but this is I'm not going to speak about this detail, so I have just something like that. This is a lamination, and well, there is some of them may have negative signs, but it really doesn't matter. So there is a kind of very geometric interpretation of the space laminations. On the other hand, this as a set, this is chi of ZT is and as any cluster variety over tropical semi-field is always just isomorphic to Z to the power certain dimension. So this is a kind of, it gives global coordinates on the lamination space. So this is a very simple space, though it's not very obvious. It's certainly more or less modification of certain construction who realized that this space, of course, well, I forgot to mention that this up to isotropy, that the space has such nice parameterization. And on the other hand, the space of chi of RT is another interpretation, original Thurston interpretation. That's a collection of, well, this is a space of measured geodesic measured laminations, or measured, one can see this foliation with singularities of sigma. Measured means transverse, foliation with transverse measure. And what is the most interesting why to study laminations? Because there is this, well, the statement which is our conjecture with Sasha, which is in general cluster situation is a partially proved conjecture, and that in the particular case of the SO2 local system is a not very complicated theorem, that there is a kind of duality. So it means that this is a so there is a canonical map pairing between this space, so well, this space chi of zt, or maybe better to write it down, yeah, with times a. You should change the Poisson cluster variety to presymplectic cluster variety, and here you make just over complex numbers, and to C. And this is a map, there is a canonical map, and so it means that the basis of functions on one space, basis here is enumerated by points here, and vice versa. So basis of the functions, you have the A of zt times there is a map of chi of C star to C, and there is such a canonical map which is well defined and gives a basis function of this space. So this is more or less well, this is all the story about canonical basis, and so for this reason it's one of the most interesting part of the story. So one really understand better what is the tropical part, and so far the only description which, well, at least I understand, is just the tropical limits of the description of tropical limits. So one can say that the first phase of the laminations, higher laminations. So higher laminations are tropical limits, tropical points. Well, points of. So points of chi of now for our cluster varieties over tropical semi-field. I will speak mainly about integral lamination. So this is the first approach to that. In order to speak about the second approach, I would like to recall some construction belonging to, well, I don't really well, certainly I learned it from Sasha and Shen, so recall. So the construction that the local systems with value of SLN on a surface sigma is isomorphic to the local systems, or also it's non-abelian local systems, it's isomorphic to abelian local systems of the cover of the surface with values in with values in the multiplicative group. And this is really, well, there are kind of many constructions. It's called habilitization, for example. Well, there are different ways to establish this isomorphism, but the one which is corresponds to cluster coordinates is given by passing to bipartite graphs, and what the bipartite graphs which were drawn yesterday by another Sasha. So I just reproduce the picture of Sasha Shapira. So here is the bipartite graph, and I draw the picture for SL3. So you triangulate your surface, then you just you triangulate your surface. Maybe I'll use another color to do that. So this the green are triangles of the surface. So now in every triangle you draw some nice hexagonal picture, and you consider this this picture. And the claim is that the claim is that your space of global systems chi of SLN is mapped to is isomorphic to the H1. This is a bipartite graph, bipartite, which, well, for every n, its own bipartite graph, every triangulation graph B, and you have H of B with coefficients in C star. And on the other hand, there is another construction, which is maybe, which I think that, well, certainly by Sasha, but for co-authors, I'm not sure. H1 of B sigma tilde, which is some covering, which is constructed out of this graph B with the value of C star. So the first construction it's kind of metroid construction. So it's, you consider this this graph is a metroid because black and white graph. Well, what means the metroid? So for every white vertex, you associate one-dimensional vector space. For every black vertex, you associate every black vertex mean that all their neighbors is a circuit. So it means that, for example, you have collection of one-dimensional vector spaces, and every three vertices which correspond to one black vertex belong to one plane. They are one dimension. Their direct sum is one dimension less than their number. So, and the claim is that for any connection, you get a realization of this metroid. So this metroid, on the other hand, gives you an abelian connection. So this is this metroid construction. Well, it's not so. I will not go into details, but the metroid construction gives you explicit morphism from here to here. And on the other hand, here from here to here, you have the graph, and from graph, essentially, you need to construct a ramified cover of your surface. And what you do, you just, this is just gluing, it's achieved by gluing zigzags, disks to zigzags. So, for example, in this particular case, zigzags are paths which go left, right, left, right. And well, if you are closed surface, which I did not draw, but these zigzags are always always closed, and moreover, they are contractible, and so you can glue a disk, and which covers your surface. Well, maybe better to glue with puncture discs, puncture disk. Disks. So, and every edge bounds exactly, well, there are exactly two zigzags passing through each edge. So you glue these disks, you get a surface which covers the original surface. And on the other hand, it's ramified at black points. In triple points, they are ramified simply. In quadruple points, they are ramified doubly, etc. So you really describe combinatorially the surface which is obtained from this graph B by gluing disks. And of course, this is gluing the puncture disk. Puncture disk is topologically a circle. So the topology of homotopy of B and homotopy of sigma tilde is the same, and therefore homology is the same, of course. So there is this isomorphism between the two, and this is well, now this construction allows to give some kind of second phase of the laminations is the following. So this is the H1. So this is a point. This one. So the next one will be the H1 of sigma tilde or B with values, instead of multiplicative group, I take the additive group. Here, I don't need, because I have just a group with respect to addition, so I don't not need multiplication. So I do not put the letter T here, but essentially this is T. So of course, it's the same thing as H1 of sigma with values of B, sorry. H1 of B with values of Z. So in a sense, tropicalization amounts to, well, passing through from multiplicative group to the additive group, and the same formula as gives you the passing from local systems to the homology. The absolutely the same formula gives you the passage from that to that. So this is a one way to see what is the the second point of view. Important detail here, that well, this isomorphism as well as this isomorphism. So I claim that this is isomorphic to a chi of SLN. I forgot to mention, but yeah, chi of SLN with values in well, with corresponding to the tropical symmetry. What is important here, that well, this isomorphism is not canonical. It's really depend on triangulation. So in particular, this space has no linear structure. However, of course, the homology space is, but this isomorphism is so not canonical that if you change another triangulation, of course, the correspondence is not doesn't preserve linear structure. However, it does preserve the piecewise linear structure. So this is a, well, this is the second point of view. Now I'll going to pass to the next. Well, and yeah, maybe I will not go into too many details. So the third picture, I will maybe need to go to the next page for that. So the third phase is the following. So it's Lagrangian submanifold. Submanifold and T star of sigma. Indeed, how pass to from here to here? It's just quite easy, because what is the Lagrangian submanifold? Sorry, maybe it's not Lagrangian covering. Not into sigma. So this means that Lagrangian submanifold, which I will still denote by sigma tilde. So now sigma tilde will be not just the sigma tilde, just covering, but I want it embedded into the star of sigma. In a Lagrangian, it's such a way that it's Lagrangian, and obviously the correspondence between the homology class is obvious, because well, once you have a Lagrangian submanifold, you can restrict the canonical form, and so to the sigma tilde, it gives you well, this is the canonical form gives you homology class, and vice versa. If you have a homology class, you take a form which represents it. It corresponds to Lagrangian submanifold. Of course, this Lagrangian submanifold is defined, not canonically defined, because it's defined up to homology class in that, and what, well, I will consider homology class up to Hamiltonian isotropy, because it's known that Hamiltonian isotropy. So this sigma tilde is a kind of it's a kind of spectral curve. So one can, and the main example of this Lagrangian submanifold is just really a spectral curve in literal sense. So spectral curve. So what a spectral curve is just the space of points in the cotangent bundle, which has just z and I'll denote by z and p. Z is point of the surface and p on the boundary, such that there is a well, sigma tilde is such that p to the n plus t n minus 2 p to the n minus 2 plus up to p to the n yes, up to t n p tn without any equals 0, and OTs are holomorphic, and TIs, of course, are just I differential, so they are in the sections, homomorphic sections of the cotangent bundle. And this is a classical object, and so this is a and of course this form alpha is just is a real part of PDQ. But there is a certain problem with that. That of course this is an example, and what I really want to study is these are integral laminations, and not and on that these laminations are very laminations corresponding to this. It's very seldom integral, because more or less the space of spectral curves has the dimension which is half the dimension of local systems, and therefore you have well, the periods are not guaranteed to be integral. For SO2, you can consider just all possible complex structure. In this case, you have good dimension, and that's you may expect to have integral laminations. But in general, this is really well, almost never alpha belongs to H1 of sigma tilde with value of in Z. So solution, which I'll which is considered well, solution is just kind of obvious. We just consider non-holomorphic curves, and what we proposed with Alexander Thomas. So you consider essentially this. Well, it's kind of tautological what I write, but I want to consider the sigma tilde now satisfies a little bit more complicated equation. Namely, you have the same thing, p to the n plus etc. plus t to the n equals 0, but you also impose the condition that the p bar is equal to mu to t mu to p plus etc. plus mu n minus mu n p to the power n minus 1. So you have two equations now. P and p bar are independent. And also the condition that the homomorphicity condition is replaced by the condition that this is Lagrangian, so plus Lagrangian. Well, it can be written in terms of T and P, and in particular, when O mu is 0, it reduces to the condition that T is homomorphic, but plus is Lagrangian. Plus Lagrangian, this is condition. So you need to this equation to Poisson commute and modulo of these equations, and this is gives you some differential equation of mu and p, mu and t. or T for given mu. And of course, well, you need to pay something for that, because this is some canonical object. So for any connection of T and mu, you have the scaling connection of T, you have a spectral curve. Here you have plenty of curves. You can act, for example, by diffeomorphism on that space, so therefore you in fact also you need to take a quotient with respect to some group, which is a group of cyclic morphism, of course, cyclic morphisms of T star of sigma, which preserves the zero section. So there is some group with respect to which you can you should quotient. Well, this is it just remarks that now we can see the laminations as Lagrangian submanifold cotangent bundle. Now I will pass to the fourth animal, and this fourth phase is the following. It will be colored W hat colored graphs. And I will explain what is that. So I want to construct, so main construction is the following. So I take, as before, sigma tilde is a Lagrangian T star of sigma Lagrangian submanifold, T star of sigma Lagrangian. And one can construct a map from sigma tilde to the product of sigma times S1. And if you take a point X, then you can associate to that the point pi of X, which is just projection. So pi is a map from sigma tilde to or T star to sigma. So it's projection of potential bundle. So pi of X, comma, the integral up to X of our form alpha. And this is this is a map. This dimension of this manifold is 2, and dimension of this manifold is 3. So we have a 2-dimensional space mapped to 3-dimensional, and therefore, in general, this map is not an emending. It can have singularities. So the most typical singularity is self-intersection points. So I can consider just the space of sense of intersection points and project it. So my graph G, sorry, gamma, the graph gamma, graph gamma, this is a projection. Well, I would denote by phi on sigma of singular points of phi. So it's obviously looks like a graph, because generic singularity is just self-intersection. So we have some one-dimensional lines, but the graph is not arbitrary, and this is well, of course, it can be really complicated, but if you consider really generic sigma tilde, you cannot expect the singularities more than some special ones. So the claim that there are 3 claim that for sigma tilde generic, gamma has either has three types of vertices. Three types of, well, has vertices, maybe. Vertices of dimension of valency. First of all, these are three valent, and it corresponds to the branching points. So sigma tilde is a ramified cover, so it's branching points. There are four valents. So you have something like that. They are four valent vertices, and they correspond to just, well, the self-intersection points, the set of self-intersections do not intersect. Well, self-intersections are lines of the image. They are lines, but they itself do not intersect. But if you project them on the base, they may start intersect. So it's just kind of what say random intersections. So random intersections and the fifth and the another version is also there are six valent vertices. And this corresponds to, well, you have 2 dimensions, 3 dimensions, you have may have triple intersection points. So vicinity is triple intersection points. And well, and this is here you have 2, and you may have 6 valent vertices. Well, but I promised that this graph is not just graph, but it's actually colored, and this is to speak about that. I'll speak a little bit about the another phase of so the fifth phase of the laminations. So the laminations, and I will come back and explain why it's colored. So fifth phase is well, maps, it's W hat local systems. And the double hat local systems, namely, you have a map from pi1 to of the sigma minus the branching points, to the group, the affine while group W hat. Well, for a moment, it's just will be for SLM. How it works? So once again, I have it's maybe easier to explain on just one picture. So if you have a surface, well, suppose we have a surface. Yeah, sorry, I will just move this. You have a surface. And consider some paths on the surface, which I will draw not closed, but mainly I will be interested in closed paths. So I have a closed path, and then I can consider the inverse image of this. So I have the map from, well, I'm trying to draw here the sigma across S1. But not, well, I will not draw the circles, but I will draw only the inverse image of the path of the base. So inverse image of the projection is just a cylinder. So it's a path over the path on the surface, and the inverse image is a cylinder. And well, now there is sigma tilde which is sitting inside, and sigma tilde intersects the cylinder by some lines. So you have some lines which somehow go along the cylinder. I'll draw, well, maybe better to draw something which goes something like that. Not good, because I do not want any. So you have some picture like that, and well, of course, there are several intersections. Some points are these paths intersect, and these points correspond exactly to the singularities of the map sigma tilde to here. So therefore, in fact, this point, for example, it projects to some point over here, and I claim that it's exactly the point where my curve intersects with the graph. So graph is just inverse image, well, the set of points where the inverse image of sigma tilde consists of less than n points. So here it's intersects. So this point is also projects to something somewhere which is passes the edge. This one as well. So you have something. You can have something like that. So you have points here, but maybe it's not a good idea to draw them with the same color. And what's the color? Well, it's more or less color reflects which points intersect. And what I want to say that this cylinders, the space of cylinders, is a nice geometric way to present. We can imagine this one as elements of the group W hat. So you have the elements of this group is the set of cylinders with endpoints on the right-hand side, endpoints on the right-hand side, which are connected in some way. The product of this group is just you attach one cylinder to another, and this obviously this group is central extension is an extension of the or this is just this W is just permutation group, so it's a permutation because you have a homomorphism. Well, you have anyway you have a correspondence between points on the left to the points on the right. And the kernel is Z to the n, so the kernel consists of all diagrams, which every point is connected to its partner, but the difference, such diagrams differ by how many times they go around the cylinder. So this is a central extension of, not well, central extension of the permutation group. And this is just the affine Weil group, and the affine Weil group is generated by, well, for SLN is generated by, so W hat is generated by the sigma i's, such that sigma I, well, with braid relations, but sigma I plus 1, sigma I, etc. So sigma I equals sigma equals sigma I plus 1, sigma I plus 1, sigma I plus 1 for I in Z over NZ. So it's cyclic generators, and of course the commutation relation also, plus commutation. So therefore, I have my edges are colored by the graph guided by generators. So the edges colored by generators. On the other hand, from this picture, it's clear. Well, I drew the point, the curve, which is not closed, just to in order to draw this, be able to draw this picture. But the draw were closed. Well, there will be a correspondence between the points on the left. On this picture, there is no correspondence between the points on the left and points on the right. But if you make it closed, because there is correspondence, so really you have an elemental W hat. So you just get a homomorphism from pi1 of the surface to the W hat. And therefore, so here is coloring. I colored. I can just add here by generators. Of W hat. And here I can add also the property that if you have triple vertex, so all of the colorings are the same. So sigma I, sigma I, sigma I. Here you have four valent vertex, and you have sigma I, sigma J, sigma K, sigma I, sigma K. And here, well, maybe I have too small picture. Sorry, I'll maybe redraw it in the empty space. So you have here you have six valent vertices. In this case, you have alternating. So it's sigma I, sigma K, sigma I, sigma K, sigma I, sigma K. So if you pass through the vertex, the sigma I depends on sigma K. Well, this is certainly just a version of this graph is, of course, a version of Andy's spectral network. It's just, well, once again, I do not claim that I invented something principally new. It's just a translation on another language, which is something existing. Well, this is a well, this is however, maybe hat is something which I added to that, but maybe not also. So you have this fifth point of view on the laminations. Well, now what is also well, once again, one should for not being homomorphic, one should pay something, and one should pay that actually strictly speaking, this is the colored graphs should be considered up to equivalence, because if you deform the graph, the Lagrangians are manifold. Of course, the graph changes, and this is up to equivalence. Yeah, this is, well, the source of all problems. Up to equivalence. And this graphs up to equivalence, well, the equivalence, there are some obvious ones. For example, if you have something like three valent vertex and another vertex which just passes through that. So this is equivalent to the same thing where you have your vertex from the other side. So this is kind of obvious thing. There are a few non-obvious. The most complicated one, which we know, we actually do not know if we know all the. Sorry, I should mention that all these activities, together with Alexander Thomas and Valdo Tatishev, well, the only thing which the most complicated which we discovered was, well, later we found it elsewhere, but nevertheless, it's if you have a square with the well, I'll draw maybe something. Six valent vertex, which is colored appropriately. So this you can change the diagonal. There is some relation. And and well, there are some more relations, and it turns out that these relations absolutely independently appeared in a paper by Ellis and Williamson, where they considered the products of the products between maps between products of Zergin bimodals. So this is really exactly the same pictures, though they have had no inner and some manifolds, whatever. It was pure algebraic, and also they have the same question. They promised that they have, but so far they didn't publish the proof that really the set of these relations is complete. Maybe I'll comment a little bit why it seems to me that these pictures have something to do with something else. It can be this approach maybe the most far away from original definition of tropical points, but nevertheless I want to say that these pictures are a kind of generalization of laminations in the old sense. So it's a collection of curves. Instead of that, you consider collection of finite of finite graphs, but now the equivalence is much more complicated than just isotopic. Some remarks about this that it has this graph has something to do with cell decomposition of the moduli space and some application of this also application in the sense that Sasha said once to me that you should start all your talks by the statement "I have a dream." So it's also something of this kind. So I have a dream that. Suppose you have a homomorphism of you have a space of local systems, so some X space, for example, I don't know, of G and G with surface sigma, and you have some elements in the local system which are not by, for example, local system X, and suppose that gamma is this colored W. Well, for the moment, let's take W colored graph, not hat. So I just do not allow colors which are colored graph. And I want to say that X is compatible with gamma if we can choose a section over every face of gamma, Galois graph on the same surface, of course, on sigma, over every face of sigma, such a way section of a flat bundle, horizontal section, of course, horizontal of flag bundles. So in such a way that in such a way that it's compatible with the in such a way. I don't want to write many words. So if you have an edge which is colored by sigma I, by A, I don't know, and here you have a flag F1, and here we have flag F2. So I want that these two flags be at the distance a. So, well, you have two flags, f1, f2, and you can send them to the space of flags, well, G over B. You can send it to the space G over B squared over G, which is, of course, this just the one group. And so I want that this one should be sent to, so this should be sent to A. So this, for example, is A. So it is described be a subset in the space of local system. So for any graph, there is this subset. And the conjecture, which is definitely wrong, but in this form, conjecture, the conjecture which has some chance to be right is just much longer. But I'll say so. Conjecture is that this equivalence classes of graph, well, maybe of graphs give cell decomposition of the space chi of G sigma. Another remark that, well, I just downgraded immediately the group W hat to the group and to the while group, and this is not well, it has some meaning, because even these graphs corresponding to, first of all, this, if you replace the group affine group by fine dimensional group, you get something, you get the composition of your fine dimensional space. On the other hand, if you upgrade to W hat, then remark that if it's true, well, another conjecture prime can be said that equivalence classes of, so this is if applied to W hat and G hat, it gives a cell decomposition which is infinite, of course. Well, maybe cell certainly cell. I mean that each cell is a product of certain number of C stars and a certain number of C's. So this is not a cell in a real sense. So cell decomposition of the homomorphism of PR pi1 of sigma to G hat, and this is a space which well, interested me quite a lot, because, well, this is definitely in infinite dimensional space, and if you consider just, well, the connection with a fine group, so no, it's not really clear how to work with the space, because it's a little bit too large if you consider just all possible homomorphisms. On the other hand, if you have such cell decomposition, you can present it really as a limit of some finite dimensional spaces, and well, it's much easier to work with just, well, of course, the dimension is not limited, but however, every time you work with something finite dimension, and this is the way how to do that. Well, there is another subject which I plan to speak about. It's in relation to Hecke algebra, but well, since this part I explained to Sasha in a last conversation, maybe I'll stop here. Conversation by phone, of course. So thank you very much, and if you have cross questions.
Let's thank Vladimir. Are there any questions from the room?
So I got interested with these green pictures. Could you explain a little bit better and how it is related to Elias Williamson? This part, what are these green?
Green. Sorry, I need to draw a nice. The colors correctly. I just didn't copy properly. Sorry, this is maybe.
What are they?
Well, this something like that. So this is like that. We think. No, it's green. The same things from this side. Well, maybe I mean, what is this for what is what we know? Well, we actually saw this picture from in their paper, and we reproduced it by writing down some formula for some Lagrangian submanifold. So the only thing they can say.
Relations, there are some relations, right?
So it means that you deform your Lagrangian submanifold in the cotangent bundle, and you see what happens to the intersection, self-intersection of this Lagrangian, of this the corresponding space in 3 dimensions. So there is some intermediate picture where you have many green and many red ones. So it's kind of honestly for me it's a little bit exotic. I asked Alexander Thomas to compute that, and he reproduced it. But I can explain very easily give a formula for a one parameter family of Lagrangian submanifolds, such that you have left picture at the beginning and right picture at the end.
But how it is related to Zergel bimodals?
They have some kind. Well, this is honestly I cannot. What they do, they take the tensor product. I should remember. What they do, they essentially take the intertwining, as far as I understand, about Zerger bimodules. Well, maybe I say something absolutely stupid, but they take intertwiners between Zerger submodules, bimodals, and they figure out for every graph. Yes, well, they have pictures which have some kind of beginning at the end. They have some Zerger modules in the beginning, some of them at the end, and they connect them in some way. And then they claim that if you have and for every such picture, they construct a homomorphism from product of on the top to product of the bottom. And then they figure out when these isomorphisms are the same. And they claim that exactly those moves are allowed.
So some of the faces of this story you described seem very specific to the AN-SLN case. Can you give some indication of how this might work for the other type?
Yeah, well, for example, these graphs, the last one is somehow what I also like about that, because formally you can do it for any group. And moreover, you can do it for they also give it for they have even pictures for for simply laced case, any simply laced. For perhaps for B and C they are not given, but of course the graphs you can draw for graphs you can automatically draw for any picture, because you just take the vertices correspond to relations in your line group, and plus trivalent vertex, which is just a departure somehow. So you can draw for any group, and then for relation you can of course work that because you have no, well, so far we have no interpretation of Lagrangian. Well, for B series, perhaps, well, Thomas pretends to have some interpretation as a Lagrangian submanifold, subjects to certain symmetries, and so he can really write relations for the B and maybe C series, not for D. But the graphs themselves, they work for anything. For other pictures, well, for example, just starting from this correspondence between the local systems and homology of something. Once again, it's a very nice question how to really interpret it for other series. As homology maybe which subject to certain symmetries, and well, I would like very much to know the answer, but definitely I do not know it now.
Another question here.
Yeah, maybe a very quick comment. So there is some recent work by Roger Cassels and Eric Zaslow. They consider something called waves from the point of view of contact topology. And it seems they consider exactly the same thing as you consider this.
Yeah, exactly. Yeah. I remember I've listened to the talk by Cassels. Yeah. It's the third. Well, yeah, I should have mentioned that. So all these pictures appear somehow independently. Well, I also tried to figure out if there is any direct relation between their picture and this picture. Well, their approach is much closer to ours because this is contacted topology here is kind of symplectic, so this can be done. Perhaps this correspondence can be done, but they use it for different purpose. Yeah.
Thank you.
Are there any other questions from the room? Anybody from Zoom? If you have questions, please feel free to unmute yourself and ask a question. If not, let's thank Vladimir Fock again. Let's meet back here at 4:05 for the next talk. Thanks.